Hello guys, I'm back. My name is Jeferson Costa. I'm a chemical process engineer with expertise in plant design, and today I will share with you what is battery limit, what is tie-in. Let's discuss a little bit about it. I will show you process flow diagram, I will show you pipe instrumentation diagram, and we will see how important it is to know what it is and how to identify that in engineering documentation, and much more, as I will share with you as much as I know. And to start with this live session, I always like to know where you are from. So let me know if you are from India, from Mexico, if you are from Middle East, and etc., because that is very, very nice. And sorry for the late beginning. I will start in just a few minutes. I just need to remind the members of my Telegram channel in process that I'm starting this live session, and I will share also the link to this live session in Facebook and in my LinkedIn. So once I finish that, we are ready to start, and I'm pretty sure that you will not regret that. Okay, thanks a lot. And I have seen that there are some people here with me already. So Jihad's greetings, and Mohad greetings also. Thanks a lot for being here with me, okay? Okay, links already shared in Facebook. Now I will just add to the LinkedIn and we will start. Hello, Abiyad. What is actually it means? If you don't know what is battery limit and if you don't know what is tie-in, you will find what it is in this live session. And moreover, it is very, very important when we are talking about working with plan design, because we chemical process engineers must know the boundaries of our project, and that is related to the battery limits and to the tie-ins, okay? So I'm ready to start. And guys, if you have any question, I have the chat here at my site. So eventually I'll be looking for any questions that you have, and I'll do my best to answer them. And I will try to answer some questions also in the end in this live session. So it's up to you to share your question in order that we can share more knowledge in this live session. For those ones that it is first time in my live session, I already said, but my name is Jeferson Costa. I'm a chemical process engineer with expertise in blend design, and I share my experience in the internet, in the LinkedIn, in YouTube. I have a Telegram channel named In Process, where I share my experience in audios, most often in audios, but I also share some documentations there. Everything that is free content of mine, it's available in my Telegram channel In Process. And to join the In Process, the link is in the description of this video, so you can join there. It's for free, and this is it. So let's start with what is battery limit. And I will be a little bit now smaller because I want to share you some drawings. Just a moment. Now you can see in my screen a representation of a process, and it is a depressurization process, and it is a process flow diagram. So when we start a project as chemical process engineers, the first thing that you should do is to draw your process in order that people that are involved with that has a better understanding what is going on in the project. So here I have a stream that comes from a truck, and it enters my process, and I have an isolation valve, a pre-reheating, I have a pressure valve to depressurize in the first step this gas because it is at high pressure, and after that, because of the depressurization, the temperature goes down, and I can have condensate at this process, and because of that I have a heating with cooling media, and I have a vessel separator to guarantee that I don't have any kind of condensate or liquid going to the customer. And I have a second step of the pressurization and flow control, and I have the metering, and the gas goes to the customer. So what the battery limits defines is the responsibility of the engineering team and the responsibilities of the third parties. And these third parties can be the customer, can be the equipment supplier, can be the authorities, and any stakeholder that is not inside the engineering team. So once this flag goes to the customer, in general, we don't have any kind of responsibility. And when I say any kind of responsibility in terms of design, for instance, if the customer has a check valve, or if he has isolation valve, metering, and wherever, it doesn't matter for us. Of course, that during the hazard analysis of our system, we must consider some kind of we need to consider what can happen downstream of our process, but in terms of engineering, I cannot buy a check valve to install at the customer, for instance. So the battery limit is, in general, is the limitation between the responsible for the design and the stakeholders or third parties. So my process begins downstream of the truck flag, and it finishes upstream of the customer flag. So these boundaries defines my project, it defines the scope of my project, and it is my battery limit. So it is the overall battery limits, but inside the project, we have other kinds of battery limits, and we'll see together here which of them we are the most common. So, okay. So, hi, Joy Patel from Gujarat. It's the first time that I hear this name. I will look in the Google Maps. And hi, Abida from Indonesia. Nice to have you here. Let me share with you another. This is, I'm talking about the overall battery limits. Let me show you another one. And here I have the process simulation of the process that I have shown to you. So when we start in doing our process simulation, we need to know from where we start and from where we finish. So here the NG 101 is represent what is upstream in the truck, or what is in the truck, and here the NG 400 represents what goes to the customer. So between this stream and between this one, I have my design of my system, and everything that's inside here is my responsibility as a chemical process engineer. And just to repeat again, what are outside of the battery limits, we are not responsible, although in some cases we need to consider in order to do a better design or a correct design. Let me share with you another example of battery limits. Here you can see a much more complex plant, and my battery limit is the gas going from the landfill. So I have two battery limits in this case, and the gas going out from my process after the purification, after the requirements that after reaching the requirements that the customer asked in contract. So this is the battery limit. This is the overall and this is the overview. But we need to translate that to the pipe instrumentation diagram, because here we are talking about process flow diagram, and it is just a generalization in order to let all the stakeholders and all the third parties aware of what kind of scope each one has. And when we consider that it must be built, it must be installed in the field, we need to add more information in the drawings, in the chemical engineering drawings, and we have a lot of them. For instance, I just show you the process flow diagram, but we also have the pipe instrumentation diagram. There is some other drawings like classification area, plot plan, and etc. In all of these drawings, we need to know from where we start and from where we and to where we finish. So some kind of so now I will show you some kinds of battery limits when we talk about the pipe instrumentation diagram. So let's consider that my plant is receiving demineralized water or raw water from a supplier, because I need to demineralize that to produce steam. And I have the supplier that is responsible for the quality of the water and the treatment, and to deliver to me in the specification that is agreed in the contract. And once finish its responsibilities, we have the battery limits. So you can see here dash point line, and LB in this case is limite de bateria, that in translated to English is battery limit. So from the battery limit line to the left is a third party that's supplying my utility, and it is, in this case, it's water, but it could be cooling water, it can be air, it can be any kind of utility or raw material like natural gas. It's very common that we, for instance, in hydrogen plants, we buy the natural gas from the concessionary and it goes to our process. So the responsible for the natural gas quality is the concessionary. But once it crosses over the battery limit, I need to consider my design and moreover. So let's talk about that. So what is left from the dash point line is not my responsibility. What I need to is to have the utilities at the requirement that are addressed in the contract. But once it goes to my industrial plant, I need to have some kind of considerations in battery limits that depends on the kind of stream that I'm receiving. If it's instrument air, if it's cooling water, if it is natural gas, and etc. So in this example, and it can vary from company to company, but most often all companies use this kind of requirement. I need to have an isolation valve, because if for any reason I want to do some kind of maintenance in my plant, I don't need to rely on the supplier operations to stop delivering or feeding my process. So in this case, if I close this battery limit valve, I stop the supplying of raw water, and with that I am able to do the cleaning of my pipings, to do the inspection of my equipment, and etc. And there is here, you can see that there is a figure here two cycles, and one is black and another one is white, and a trace here, and it means that we have a figure 8. And the figure 8 is a kind of hack that is used to guarantee the full isolation of the valve. Let me see if I find figure 8. Figure 8 to share with you. Here I have a nice one. So here I have a figure 8, and you can see that it has a part that full solid, and the other part that it has a hole, and this hole is depending on the size of the pipeline, because when I fit this to the process, it means that I have a full flow in the pipeline. If I shift this or if I rotate this to my pipeline, I isolate the pipeline and I am not able to fit anything to my process, and with that we guarantee that the process is isolated from any kind of fluid. And that is very important when we are talking about flammable fluids and when we are talking about the toxic and corrosive fluids. So in some cases it is very important to consider this kind of fitting, because you just need to turn around the fittings and we have the isolation of our battery limit. In other cases, we don't use the figure 8. We use only raquete. Here you can see, let me see how is raquete in English. Yeah, it's racket. So we can, to do the isolation of the pipeline, you can see here, we can install a racket, but different from the figure 8, it cannot be installed at the battery limit all the time. So we need to store that in the maintenance field, and once we need to do the maintenance, the bolts are disclosed, are removed, and we add the racket. But in the figure 8, it's always in the field. So in some cases, some companies prefer that because we don't need to look for a racket, okay? So this is the first thing that is important to you know about the battery limit, is to how you can isolate that from the customer or from the supplier in order that you can keep your plant safer and do all kinds of maintenance that you need to do in your facility. And of course, depending on the pressure or depending on the process conditions, pressure and temperature, between the isolation valve and the figure 8, we have in this case here a drain to guarantee that before we close the bolts to turn around the figure 8, we drain this branch, we drain this, and we can verify if there is any kind of leaking in the isolation valve. If it is a gas, for instance, it is very important to verify that. and instead of having a drain valve, we would have a vent valve. And another thing that is very, very important to have at the battery limits is ways to verify if the customer is supplying what is in the contract. And for instance, when I am supplied by the supplier, and in this case in the raw water, what I am interested to. I am interested in the pressure in this case, because depending on the pressure that is supplied, I need to consider to adding a boost pump or a vessel to accumulate the liquid and to pump to another point of the process. And most often the pressure is one of the requirements that is set in the contract with suppliers and with customers. Just to let you know, if you are talking about gases, if we consider that, for instance, we need to reach 5 bar G at the battery limit, and for any reason the supplier is feeding with 4.5 bar G, and we have a system, a compression system, the compressor efficiency will be lower, and the gas delivered to the process will be lower, especially if we are talking about volumetric compressors. So that is why very important to have means to measure the utilities and the raw materials that you are receiving at the battery limit. And in this case, for this company, we need to have a flow indicator, or in this case is a flow transmitter with a flow indicator, in order to register the amount of stream that we are receiving, because that will be converted to the billing. So if I receiving 1000 cubic meters per hour, and it will be accumulating once that in the end of the month, or depending on the contract, after a period of time that will have a billing, in order that you will need to buy for the feedings that we are receiving. And of course, we need to consider that the same when we are delivering the gas or delivering the liquid to the customer. We need to guarantee that the pressure is okay at the battery limit. So in many cases, we will add pressure transmitters or pressure indicator to adjust our process, in order that in the battery limit with the customer, we will guarantee the contract. And also, although the customer may have its own flow measurement, we also have flow measurement at our sites to do the cross check between the customer and the supplier. And of course, that may have is small differences, but it cannot be 50% or 100% of differences between the instrumentation. And when we have here water for refrigeration, so it is very similar to raw water, but you see that in raw water we only have pressure and flow. In the other hand, in the water refrigeration, we have pressure, flow, and temperature. And that we have temperature because it's very important to a cooling system that we know what is the temperature that we are having our feeds. Because if we have a contract, for instance, for 30 Celsius degree water temperature be feeding to our process, and this water comes with 40 Celsius degree, the performance of our process will be different, and in this case it will be much worse than we imagine too. It is the same for vapor. When we contract vapor, there is a requirement for pressure and a requirement for temperature also. So In the instrument air, we have pressure and temperature, and it in general, it is the return, the cooling water return, but we have the pressure for the instrument air, we have the flow for the instrument air. So this is the kind of vision that you must have when you are starting developing your pipe instrumentation diagram. You need to understand what are the variables that are important to your process, and you need to understand the contract in order to add the instrumentation necessary to guarantee the verification of the requirements in the contract. And if we are talking about raw material, for instance, we probably will need to add an analyzer or dew point analyzer and so on. So this is it, what in general, how it is. And when we buy our equipment, and as much complex is the equipment, the instrumentation, control valves, PSVs will be supplied for the manufacturer. So we need to be able to identify what kind of connections are needed with the supplier and what is supplied by manufacturer, in order that when we do the pipe instrumentation diagram, we know what is the scope of the supplier and what is the scope of the manufacturer. So let me share with you a screen, drawing from a compressor. So here I have a compressor, and to start with, we need to identify the battery limits, or where it starts and where it ends. And you can see, just a moment, please. So you can see that each letter that I have in my drawing, and I have a connection list here, it means a point of connection with my process, and it is where it starts and it is where it ends the battery limits with the supplier. So here, when I get this flange from A, it's not the responsibility of the compressor supplier, but from this flange to the right, all of this is responsibility of the supplier. So this PIT, this pressure indicator transmitter, must be supplied by manufacturer, and if it arrives at my facility and if it's broken, I will not responsible for buying another one to replace that. I will ask for the guarantee, and the manufacturer will be responsible for replacing that while we are in the guarantee period. But we have here, for instance, the PSV, and the PSV is supplied by the manufacturer, but of course that the pipeline downstream of the PSV is not its responsibility, because it depends on the requirements of my facility. If it goes to a flare header, if it goes to a vent stack, if it can be released to atmosphere or not. So in this case, the manufacturer only indicates where is the connection with the process. So the battery limit with the third party ends here. And the same for the cooling water system, because just to remind you, I have here a reciprocating compressor, so I have a suction bottle to do the amortization of the cycle, the pumping of this compressor, and it goes to the first stage of compression. And as I compress the gas, my temperature increases, and to prevent the damage, to guarantee the integrity of the materials, I have an intercooler, so the gas is cooled, and because of I'm cooling the gas, if it is saturated, I need to have a separator. But in this case, this gas is fully dry, so I don't need to have this kind of equipment between stage 1 and stage 2, but I cool down that to prevent the damage of the second stage. And in the second stage, I compress again, and you can see references for pressure and for temperature, and it increases more than 100% in Fahrenheit, so it goes inlet with 100 Fahrenheit and goes outlet to 286 Fahrenheit. And before sending the gas to the process, I have an aftercooler that will decrease the temperature, and of course I have a temperature indicator transmitter to verify the efficiency of my equipment and if everything is okay. I have 2 points of delivering the stream. One is to the process, and it is the B, and the second one is, for instance, if I need to release this, so I send it to a depressurization system in order to be able to do the maintenance of my equipment, because it will get gas from lower pressure to high pressure, and once I stop that, in some cases I have automatic valves to do the isolation of the equipment, but in this case I have only manual. When I need to do the maintenance of this equipment, I will close the inlet valve, the outlet valve, and all the content that is inside here must be released and safely released to somewhere. And I will use this valve here to release to my vent stack or to my flare system, in order that after that I can add nitrogen to the system. So this K is inert gas inlet nitrogen purge, because I need to release any kind of flammable gas. In hydrogen is very, very dangerous, and I need to release all content of hydrogen in this case, in order that I can open any kind of flange to do a maintenance in the heat exchanging, or if I need to replace pieces in the equipment, the compressor itself, and etc. And of course that I need some kind of in this case I don't know if I need to instrument air, but I have some kind of purging here, so you can see that there is a connection for head integrity system. And this evaluating this when we are doing or developing the pipe instrumentation diagram of the project. And remember that we are responsible from the starting from the ending of our process, but between the starting and the ending we will have many kinds of equipments, and one kind of equipment can be the compressor, but we will not design each piece of the equipment, the compressor equipment. We will buy from a supplier, and according to the drawing of the supplier, we will know and we will understand what kinds of connections, and it is inside battery limit, let's say something like that, what kind of requirements I need to have. And once we transfer this drawing to the overall pipe instrumentation diagram, we'll have something like this. let me show you another compressor drawing. It's not the same kind, but the concept is the same. Here I have the drawing from the supplier, so he is only worried about what is their responsibility between the flanges, inlet flanges and outlet flanges. But in the plan design, we are worried more than that. We will add this equipment to our process. So once I add that to our process, I will limitate the scope of the supply of the compressor manufacturer. So you can see that I have a dashed line and a EU key that means equipment. So everything that's inside the E key is the responsibility of the supplier, and I know that based on the supplier drawings. So you can see that we have flags going into the drawing, and we have connections going out from the EU key boundaries. So for instance, this instrument here, this TE, that's temperature element, it is outside the E key. So it means that the project, the instrumentation engineer from my project, from my team, are responsible for buying this. If I don't buy this, it will not be delivered to the field, and if it's not delivered to the field, it cannot be installed, it cannot be commissioned, and I will not have reference for the outlet temperature from the heat exchanger. On the other hand, the T2502 is responsibility of the supplier because it is inside the EU key dashed line, and if it doesn't go to the field, it means that I need to push, or it will have a penalty to the supplier, to the manufacturer, because they must supply this instrument. I will not worry about that because it's not a scope of the design team, it's the scope of the manufacturing team. And when we are doing your piping instrumentation diagram, that is very, very important that it is very, very clear to the design team, because the instrumentation guy will look for this drawing and he knows that I need to buy this. I don't need to worry about it. You can see that there is automation here, representation in a panel or in the control room. So every piece of drawing that you have in the pipe instrumentation diagram means something. And if instead of adding the heat exchanger inside the battery limit of the supplier, you get that to the outside, it means that you need to buy the equipment, and that can be a very very, very important to be sure that the interfaces, the battery limit between the customer and your plant is okay, and between the suppliers and your design is okay also, to have any kind of misunderstanding. And guys, if you have questions, please let me know. Did you ever heard about battery limit and how important it is to plan design? Let me know. It is a kind of subject that I didn't learn during my graduation, for sure. Although I have seen pipe instrumentation diagram, the teachers didn't get too deeper on them. And when we starting in a job, in a plan design job, it's very important to have this kind of vision and the importance of the what you are doing. So that's why I'm sharing with you this kind of information. And if you are a chemical engineer to planning to work with plan design, there are much more activities to be done than just the process simulation. The process simulation is just a very small part in plan design. So here we finish here, and now I'm ready to go to the tie-in subject, and we'll talk a little bit about what is tie-in. We start with what is tie-in. Let me show you another pipe instrumentation diagram. This one is done in AutoCAD, and of course that I remove all the stamps, okay? It's not important. And here you can see that there is a skid battery limit. So everything that's inside of it is installed in a skid, and that what is outside can be installed in another skid, because you can see that there are other boundaries here and other boundaries here, but that is not what I want to show you. I believe that you already understood what is battery limit. What I want to show you is that when you have an existing facility, sometimes to increase the performance of the plant or to comply with the regulations, we need to do some kind of changes. We need to add another heat exchanger, we need to add an isolation valve, we need to remove some kind of equipment because it's obsolete or something like that. And the tie-in or the tie-in point is what represents the connections between what is existing and what is new. So when we say that we are doing having a tie-in point, or abbreviated at TP, tie-in point, or in some cases TP can mean also termination point, it means that we need to do some kind of intervention in the existing facility to add a new component. And it is very more common in pipelines when we need to do the cutting and the welding of new pipelines to expand or to update the process. And here between this heat exchanger and this observer, in this process, I need to add another equipment. I need to add another heat exchanger, and to do that, I will need to identify the tie-in points in order that the pipe engineer are able to go to the isometrics or to the piping plan and verify where he or she needs to consider to cut the pipeline. So how I will address that in the pipe instrumentation diagram? So what I do generally, and most companies do, is use bubbles to identify that. So you can see, let's just me do a zoom in. You can see that is the same process, but in the second one, between the heat exchanger and the observer, I have a new heat exchanger. And of course, I have pipelines, I have some instrumentation, and it is because of the evaluation of the process, the safety of the process, etc. But what matters most here is that between these two equipments, I adding a new one, and because of that I need to identify the tie-in points. And here I have the TP027, and it means that I need to cut the pipeline here to add this new system, and I have the TP028, and I will cut the pipeline here to do the connections between the beginning of the new system and the ending of the new system. And this is what tie-in point means. And the tie-in point can be done by many ways, depending on the kind of process and depending what you are adding to the process. For instance, if it was a cooling water system and I just want to add a new branch to my cooling circuit, I could use the hot tapping procedure to add a new pipeline. In this hot step procedure, I don't need to stop my process, because in this case, to add this new equipment, I need to stop my process. I need to drain everything that I have in this system. I need to purge that to guarantee that I don't have any kind of flammables. And once I do that, the mechanical will go here and will do the cuttings to the pipeline. And of course, when we are doing that, this is a process, or this is a activity that can produce sparkles, and it produces heat. And to avoid any kind of risks, we must guarantee that we don't have any kind of flammable here. If we are talking about corrosive, or if we are talking about dangerous streams, is the same. We need to guarantee that is empty. But there are some processes like cooling water that we just want to add a new branch, and instead of stopping all the facility or all the process to do that, we have alternatives to connect the pipeline while the system is still running. And sometimes we consider to do this kind of procedure, and of course that it is more complex than this one where we stop the production, because once we stop the production, we lost money, and sometimes it gets many hours to restart a process. So it's a kind of economics and technical issue that must be evaluated in order to be able to decide what is the better way to do or to install the tie-ins in an existing plant. So with this, we cover both subjects. Let me get bigger again. It is not a kind of subject that is very interesting, but I'm pretty sure that is very, very important to everyone, to every chemical process engineer that wants to work with plant design. And if you have any question, just let me know. Here is around 10 a.m. here in Brazil, so I will start my day. So guys, this is it. Thanks for your patience. Thanks for being here with me. And I'll see you soon in the next live session. Bye-bye.